Alright, hello. Welcome to Try 3. This is our first lesson for Try 3. And we're diving into exponential functions. I like exponential functions a lot. I think they really relate to things in the real world. And see, 2 lessons from now, we'll start talking about that and looking at exponential functions in real world problems. So let's go ahead and just talk about the difference here. Try 1 and 2, we focused a lot on linear functions. So where we have lines, we graph lines. We have linear systems where we have 2 lines on a graph. And I want us to remember that a linear function means that the set of coordinates has a constant rate of change. And when I say rate of change, remember that means like for every x like changing by 1, my y is consistently changing by the same amount. So this also means a constant slope. This also means like a constant thing being added or subtracted. So on a table you might see us like adding by 3 each time or subtracting by 2 each time as we go down our y values. Now exponential functions have something else that's constant. And what's constant here is what we call our multiplier. Something that we're multiplying by, or something that we are, which can be a whole number or a fraction. Now when we graph exponential functions, we can see a lot of different things. You could see something that looks like this. You might see something that looks like this. Heck, we might see something that looks like this. I don't like that one. Now these 2 are going to be the main 2 that we focus on, but anything that has this like curve to it and both sides like kind of flatten out, or one side is in one gets as straight as possible, those are going to be our exponential graphs. Non-examples would be obviously a straight line. That's what we learned in Try 1, Try 2. Those are lines, so they are linear, not exponential. Or something that looks like this also is not exponential. So again, this is linear. This one right here, this is what you learn next year. This is what we call a quadratic. So any sort of like U-shaped, no matter how it's turned, is what we call a quadratic. Any kind of like J or L shape, no matter how we rotate it, is an exponential function. Now, there's our graphs. Let's talk about how we can see it in our table. Well, remember, like I said, exponential functions have a constant multiplier, so a constant thing we're multiplying by. So if we look here at this table, we're going from 1/2 to 1, 1 to 2, 2 to 4. So for this table, we have something that's being multiplied by each time, and that is 2. 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. We're multiplying by the same thing every time as we go down our y values. So that would be exponential. Same thing over here. To go from 3 to 1, I'm subtracting 2. But to get from 1 to 1/3, I'm not subtracting 2. Remember, that would be something that's linear when we're subtracting the same amount each time. So now we're going to check what we could multiply by. Well, to get from 3 to 1, we multiply by 1/3. Now that's the one tricky thing with exponentials, is that sometimes our multiplier is a fraction. But don't let that scare you. A way that I like to do and figure out what my multiplier is, especially if I notice my numbers decreasing. Well, number one, as you go down your y's, if your y values are getting smaller, you have to be multiplying by something less than 1. So we know it has to be a fraction. But now it comes to figuring out what number has to go on bottom. So to figure out the denominator, just figure it out backwards. What do I multiply by to get from 1 to 3? Well, 1 times 3 is 3. So that's our denominator here. So we're multiplying by 1/3 each time to get from 1 to 1/3. 1 times 1/3 is 1/3. To get to 1/9, 1/3 times 1/3 equals 1/9. So again, our multiplier for exponential tables can be either whole numbers or they can be fractions. If you notice your numbers are getting bigger on the way down, it'll be a whole number, so figure out what number you're multiplying by. If you notice your numbers are getting smaller going down, then it's going to be a fraction. And to figure out the denominator, again, just go backwards. 1 times 3 is 3, so 3 goes in the bottom. These would be non-examples. So again, 3 options here. We have, it's either linear, a constant slope, a constant rate of change, a constant thing being added or subtracted, exponential, or we're going to just call it neither. So for this one here, to get from 0 to 2, or sorry, -2 to 0, we can either multiply by 0 or we can add 2. To get from 0 to 2, we also add 2. So here, we're adding 2 each time. So this one would be linear because we're adding something each time. For this one, well, to get from 1 to 0, 1 times 0 is 0. But then 0 times 0 would be 0. So that doesn't have a constant multiplier. So now we'll check to see if we have something being added or subtracted. Well, if we go from 1 to 0, that's -1. And then from 0 to 1 is +1. So already we don't have a constant slope. We don't have a constant rate of change. We're not going up by the same amount each time over here. So this one would be neither of those things. There isn't a constant multiplier. There isn't a constant number being added or subtracted. So we would say this is neither. Okay, so going forward, key things that I need you to be able to do today are, number one, to be able to look at a table and tell me whether it's exponential or not. So you need to be able to do what I just did. Look at a table and figure out if it's being multiplied by something as you go down, or if we're adding by something or subtracting by something as we go down, or if it's neither of those things. There isn't a constant. Then that would be neither. So you need to be able to do that. And then this is the other thing that you need to do. So let's take a look. Creating equations. So linear equations we spent a lot of time with were that y equals mx plus b. Exponential equations are y equals a times b to the x power, where x is our exponent and b is our base, meaning the base of our exponent, the number that we're using the exponent on. So let's go ahead and talk about what each of these variables mean. Well, x just represents some x value. Similar to our linear equation, y equals mx plus b. Remember, x was just an x value from our x coordinate. Same thing goes for y. Y just represents some sort of y value. Now, a and b are the new things here. So a is what we say our starting value. for our y-intercept for this graph. So those are flipped around here. So A is our starting value for exponentials, and then B is that phrase or that term multiplier that we've talked about, that constant thing our table or our problem is being multiplied by. Ooh, multiplier. So again, we have A as our starting value, and B is that constant thing we're multiplying by. So again, examples over here. This would be exponential because we have our starting value. We have that number that we're multiplying by each time. And then the key things here are that x is in your exponent. In order to be an exponential function, your x has to be in your exponent. Over here, that's why these fall as non-examples. X is down here, not as an exponent. This is actually a linear equation. We could say 2x plus 0, 2 is the slope. And then this one, again, is non-exponential because the x is down in my base and not in the exponent. So the 2 and the x would need to switch places in order for this to be exponential. And then this one over here is also exponential because, again, x is in my exponent, 2 is the base, so 2 is the multiplier. And then there's nothing there for the starting value. Remember, that just means it's 1. Alright, so now let's put this to use. So I have it color coordinated over here, and we have our table right here. So to create the equation of this table, I find this a lot easier than linear equations. So let's look at it. So remember, A is our starting value. So we're looking at where our x is 0, that's our starting value. So I'm going to do that in red. So when x is 0, my starting value is 1. And then we need to find our multipliers. So what we are multiplying by each time. Well, to get from 1 to 2, we multiply by 2. And 2 to 4, we multiply by 2. From 1/2 to 1, we multiply by 2. So there's my multiplier. Now we can go ahead and create our equation. So we're going to have y equals our starting value, A, which is 1, and then our multiplier, B, and then don't forget your exponent. Again, it goes A and then B in our equation. A is your starting value, so that starts your equation, and then B is your multiplier. So let's look at one more problem. There's an outbreak of a zombie virus at Cole. Initially, there was only one person at Cole who was infected, Victor. Each zombie infects 3 people each day. So we have created this table here. So we have Victor is infected, and then he infects 3 people. Those 3 people infect 3 people each. So 3, 3, and then 3. So we get 9, and so on. And we're going to grade our equation. So again, we need to find our starting value. So how many started as being infected? And then we need to find our multiplier. So starting value, again, is how many we start with. In this case, we only started with Victor. So 1. And then figure out your multiplier. How many are we multiplying by each time? Go ahead and take a second and figure that out. And we're multiplying by 3 each time. 3 times 3 is 9, 9 times 3 is 27. So we're going to have 3 in our parentheses and then our exponent. Now there's a CFU here. If 2 students were turned into zombies initially, how would the equation change? Try answering that. Alright. The only thing that would change is our starting value. Instead of having only Victor start, we're having 2 zombies start. So we're going to change that starting value. go ahead and work on independent practice.